Welcome to this video lecture on the subject transmission lines and antennas. So in this lecture we are going to discuss about line at radio frequencies. So the line at radio frequencies of above megahertz values, so some of the assumptions are taken. Very considerable skin effect, internal inductance is 0 because of the skin effect, and omega L value is greater than R because of high frequency. So it is to be considered while calculating the impedance value, and conductance is 0. So in case of open wire lines at high frequencies, the current is flowing on the surface of the conductor in a skin of very small depth. So since the internal flux and internal inductances are reduced to 0. And in case of coaxial cables, the parameters of the coaxial line are also modified by the presence of high frequency currents on the line. Because of skin effect, the current flows only on the surface of the conductor, that it eliminates the flux linkages. And the capacitance of the coaxial cable is not affected by the high frequency current. So for the line of zero dissipation, for transmission of energy at high frequencies where the power and efficiency is high, assumption of negligible losses or zero dissipation can be used in the analysis for the transmission line, also known as the perfect lines. So we consider R equal to 0 and G equal to 0. So the line parameters for the line of zero dissipation are given, where Z is the impedance value, it is j omega L. Here R is assumed to be 0 and Y equal to j omega C. In this G is assumed as 0. So Z0 is calculated as square root of Z by Y. So we get square root of L by C. Similarly, propagation constant gamma, it is alpha plus j beta, and alpha is 0, so beta equal to omega root of LC. So velocity is calculated from ratio of omega by beta, so we get 1 by root of LC. So these are the conditions for the line of zero dissipation at high frequencies. So here we are going to discuss about standing waves, because the standing waves are important concept in the transmission lines. When the transmission line is not matched to its load, that is the load impedance is not equal to the characteristic impedance, the energy delivered to the load is reflected back to the source. So this combination, there are two waves, incident and reflected waves, as shown in this picture. So there is original signal and reflected signal. So this combination of the incident and reflected waves gives rise to the standing waves. In standing waves, there are nodes, which that is points of zero voltage or current, and antinodes are the points of maximum voltage or current in the standing wave systems. A line terminated in its characteristic impedance has no standing waves and thus no nodes. So this is called as a smooth line. So standing waves are important in the case of impedance matching. Here we can see the standing wave on a dissipation line terminated in a load not equal to R0 in the first diagram. So in the second diagram, it is standing waves on a line having open or short circuit termination. Here the nodes and antinodes are noted. And in the first diagram, the E max and E minimum values are given. So this is used to calculate the standing wave ratio. So next, standing wave ratio, it is given by the ratio of maximum to minimum magnitude of voltage or current on a line having standing waves is called as the standing wave ratio. So it is either V max by V minimum or I max by I minimum. So maxima of the voltage occurs at which the incident and reflected waves are in phase. So it is given by this relation V max. And minimum of the voltage occurs at which the incident and reflected waves are out of phase. So V minimum, so this used to calculate S value. S is standing wave ratio. So V max by V minimum. So from the previous two equations, we get 1 plus K by 1 minus K. And K is given by SWR also. So, and V max minus V minimum by V max plus V minimum. This is one of the relation and another value, it is can also be written as gamma, as the given in this symbol as like half of the t, this gamma. So reflection coefficient is VSWR minus 1 by VSWR plus 1. So these are very important relations in case of standing wave ratio and reflection coefficient. Next, voltage standing wave ratios and antennas. So why it is important? That is, standing waves and standing wave ratios are important. So impedance consistencies, inconsistencies in radio frequency electrical transmission lines can cause power dissipation and energy reflection. So whenever this dissipation or reflection occurs, we consider VSWR value. So voltage standing wave ratio serves as the method for accessing the flaws in the transmission line. So illustrative instant is a power amplifier linked to an antenna or transmitter via a transmission line. So consider this case. A higher voltage standing wave ratio signifies the reduced efficiency of the transmission line, so harming the transmitter and reducing its effectiveness. So in the industry, antennas are often evaluated based on the VSWR specification. So this passive measurement method quickly determines if the antennas are properly tuned. So antennas VSWR as a function of frequency is recorded using a network analyzer. It is important to note, while VSWR indicates how much power delivered to the antenna, it doesn't guarantee that all the received power is radiated. So therefore VSWR accesses the antenna's potential to radiate. Okay, take the assessments. First question, given that the reflection coefficient is 0.6, so find the VSWR value. And second question is, the maxima and minima voltage of the standing wave are 6 and 2 respectively. So here the Emax and E minimum are given values. So find the standing wave ratio. So let's see the answer in next slide. So in the first question we need to calculate the SWR value, but we have given with reflection coefficient 0.6. So the relation is S is equal to 1 plus K by 1 minus K. K value is 0.6. So the answer is 4. Option B. The second question is, the maxima and minima voltage are 6 and 2. So standing wave ratio is V max by V minimum. So this is answer 3. So answer is B. Thank you for listening this lecture.